Sit down. So okay, so what I was going to do now is application of icon marks with two cases, two scenarios, and how they can be used in different ways. And these are more related to galaxy formation problems, because that's primarily where I work in that sense. And so we're going to consider two, and depending on the time, it will be two or just one, and the other one will be done tomorrow. So the first case is what we discussed in a Farah et al. Paper, which is the galaxy clustering in gamma as function of galaxy properties. And the point of there is actually to use the marks as a test of the published Galford models against the data not used in model validations. Yeah? So actually testing how well do the models do when compared to data. And then identify the aspects that needs to be improved in Galform. Yeah? And that can be done to be addressed by new Galform models and so on. That's one example of a case scenario. So it's more used as interpreting the data in terms of a model and so on. In Robotham et al., which present the galaxy groups in gamma, or how to do it, the aim there is to use the marks to tune and validate a group finder algorithm. So that's a completely different aim of using the marks. We just want to make sure that we understand how it works and so on. To actually understand the limitation of the group properties we get from this group finder. So it's two completely different applications of marks, which are both valid in their own rights and have, and so on. So that's just going to go through with the Farah et al. Work. So first of all, the one thing I want to mention here is the stellar masses. Yeah, so it's inferred versus true. This is a cautionary note that we have in this paper, is the fact that we know that observation in gamma, for example, the stellar masses are inferred from galaxy colors. Yeah? And there is a relation which had been derived using SCDs and SSP models in Taylor et al. That we have a relation between the stellar mass of a galaxy and the colors, which is given by this relation here. Yeah? And there's a color information and absolute magnitude in the I band and so on. I just want to make you aware of one thing here, which theorists are kind of like always confused about, and observers equally much, is how this little h scales around and moves around depending what you're doing. Yeah. So observationally, stellar mass scales with h to the minus 2, and that comes simply from the fact that you're observing photons. You're actually transforming a light into a mass. So actually that's the link to it, the h to the minus 2. It actually comes from the fact that luminosity is h to the minus 2 links. But if you run a simulation, your stellar mass is h to the minus 1. Yeah? That's fine. Now, all of these small things you need to keep track of and think about how to do it. So whenever you see stellar mass in h to the minus 2, you can ask two questions. A, is it a typo? Or where does it come from? Yeah? And then you will have to think about it more carefully. Yeah? So what we did here, we just an example here on the Farah et al. We just decided to see what is the true stellar masses. Now we have scaled the true stellar masses in the Galford model to be in this h to the minus 2 units, just making sure they actually multiply, divide. Now that's how we'll tell. I'll leave it to you to figure out which one it goes to get to the right stellar masses in these units, and you compare it, the inferred and the true, having used this color information. Now, the reason we did this is because we assume here that a galaxy information model is like the real universe, because that's our starting point where we think we've done a good job with the model. The two things which shows up is actually the two different models considered, Gonzalez Perez 14 and Lacey 15, is actually, you have different effects on these stellar masses. You have a large scatter in these stellar masses, yeah? And they're different for two models. And the other thing which is what the magnitude of the differences in using this relation. It's of the order of 0.2 to 0.3 dex in scatter, and depends on the stellar mass values. Yeah. So this is low stellar masses, high stellar masses. This is typically your Milky Way galaxies around here. Yeah. And red and blue is for red galaxies and blue galaxies. So you actually see that this is something which impacts what is your inferred stellar masses, just assuming what you have been doing. Yeah. Now, in Farah et al., we actually use the true stellar masses in your analysis. We just want to see what was the impact of just assuming the color information to derive a stellar mass. So you have a feel for it. And what we didn't expect, maybe, to see the large variation between two models. Yeah? That's why we did it as well, to present it this way. Impact on clustering is discussed in a whole different paper, Campbell et al., and so on how you have the stellar masses, if you have inferred stellar masses, and how you select your samples, and so on. And they have impacts of the order of the 10 to 20% level, and depending on what you're doing, and so on. And it's just because you need to make sure that you're actually comparing like for like. Now, the color distribution. So that's a very straightforward plot. You can do this in the mark. And now, why do we do this in the mark and not in the galaxy information directly? So in the galaxy information model, the only thing we have information at a given redshift. We don't have it as functional redshift. But if you look at a survey, it has information from low redshift to high redshift. There's a selection function in there. So with the mark, we can actually probe it in the same way, making a like-for-like comparison on how it looks like. So up here, you have the color distribution of as functional luminosity for our gamma galaxies, the flux limiter there, and this is for the models. You don't need to be very accurate or very detailed here to realize colors do not do a good job in Galform. Yeah. So it's something we knew, but it's actually very nice to be able to quantify it quite precisely, doing like for like discussions here on what needs to be done. The main difference here is actually that the bimodality between red and blue is so much more stronger in the model than it is in the data. And there I put my, here I'm like the observer, and I tell my Galform friends in Durham, you need to think about your modeling a bit more and sort it out. And then you have the people coming up with lots of different models, trying to figure out and so on. And that's what they're working on, trying to improve the models. Yeah. So this is, here I'm taking more the back seat of comparing it and understanding the limitations of it. Yeah. As opposed to trying to solve the problem. Yeah. Now, when you do a flux-emitted survey, you have a selection function. And then there's a lot of ways for modeling selection function. And here we actually use an intrinsic modeling is using cloned galaxies and winded randoms. And so as described in the paper, it's actually building on the Cole et al. Model. And the main reason for that is that we actually can create now one set of randoms for all our gamma galaxy samples. Because what we have done is actually take our gamma galaxies and we clone them in a way to preserve the luminosity functions and the number density evolution in the survey. And what you can then afterwards, you have a random catalog as opposed to, most people are used to a random catalog which just is position on the sky, X, like RA deck and redshift, that's my randoms. This randoms comes with X, Y, Z, or RA deck and redshift, and a galaxy ID, which is a gamma galaxy. So each of our randoms have a property. Now the nice thing with that is now I can start slicing with this one single set of randoms, my data up in all different properties I want. And in solid is the histogram as functional redshift of the N of Z of different galaxies of different luminosities in gamma, and the smooth dashed histograms are the corresponding randoms. Now, the nice thing here, as I said, is just there's one set of randoms for all these samples. I split it by luminosity, or I split it by stellar mass, I get it right. That is very nice because when I do cross comparison between samples, I don't need to worry about how well did I do the modeling of my selection function for one set of galaxies and another set of galaxies, because I get the modeling of a selection for all the galaxies through all the properties in one go. And so that is what you get by doing these one set of randoms about the cloning. And they're windowed because what we're doing there is, if you think about it, a bright galaxy at low redshift can be seen over the whole redshift volume. Yeah, because it's bright. I can just move it further out in redshift, I will still see it. The problem with that is, if I do a modeling which allows this galaxy to go out to high redshift, I need to make sure that I know my evolutionary correction and my evolution of this galaxy really well. And that puts a very strong constraint on this modeling randoms. So what we've done is the windowing is actually we only allow galaxies to be cloned over a certain volume. And so it's a bit of a technique there. But the nice thing with this is actually we become less sensitive to the whole evolution correction over the whole redshift range of the survey, only depending on how we model it over a very narrow redshift ranges. And that makes it much more robust in that respect. So typically, galaxies which are cloned at redshift 0.4 tend to come from redshift 0.4, whereas galaxies which are cloned at redshift 0.1 are only coming over a smaller redshift range. And they're cloned over a volume, which is important because you want to make sure that you don't bias a sample as function of redshift. So it's the volume which is the intrinsic part to clone them over. But the nice thing here, you have a set of selection functions. When you have your selection functions, now you can compute your correlation functions. You just follow the procedure we did yesterday, measuring the project correlation function, which is the integral along line of sight of your the psi rp pi, and you divide it by your reference correlation function so that you can focus on the details. Yeah. And here you actually see in color is the two mocks, the Lacey and the Gonzalez-Perez model, and the data is here from gamma in the black lines. And what's important to realize is here we have the error bars, and by doing a covariance matrix analysis where we actually worry about the stability of the covariance matrix but also noise in covariance matrix, it's actually only in this sample, where the data is clearly incompatible with the measurements. Yeah? In nonsense, what we measure here is that there is less than a 2% chance that these data sets are compatible with this, that the data set is compatible with these simulations. Yeah? Or the simulation is compatible with data. In all the other cases, actually, they are compatible at a higher level in that sense. But they're not, and you need to remember how errors are correlated and so on. So it looks visually much worse than it is in reality. Now, the one thing we've done here to make it easier to visualize is these are volume limited samples. But because I've actually done my modeling of the selection function here as function of the whole redshift range, I don't need to limit myself to volume limit samples. I can use all the galaxies which are in these stellar mass ranges or in these volume or in luminosity ranges. And that also makes sure that I actually can test the model better, especially when you have limited data available, limited number of galaxies, limited volume. Because what drives these error bars is the fact that you have a very small volume to compare with. Oops. And you can do the same exercise in case of stellar mass. Now these samples are not perfectly volume limited in stellar mass. And there's a couple of reasons for that. Your selection effects, your selection is done in the R band because this gamma is done in the R band. And so you have a clear cut in the probability of finding an object of a given luminosity at a given redshift. In terms of stellar mass information, that's not clear because there's a scatter between stellar mass and R-band luminosity. And that means that there is always a small fraction of objects that could not be volume limited. So if you really want to make sure that all your galaxies are volume limited, you end up with an absolutely ridiculously small redshift range because you're going to be dominated by the few objects which have a very large mass to, like a large mass to light ratio or small mass to light ratio, depending which way you drive it. And so these samples are what we call 98% volume limited, means that 98% of the galaxies are volume limited in these ranges, but there are 2% of the galaxies which are not. And so we did some tests as well. We can test that with the marks to make sure that that is how you can make these comparisons right. And here you can see that actually at some level the differences between the model and the data is actually quite large to some level. You can see here typically what you see, the models do not have the right clustering amplitude on small scales. On large scales it's okay-ish, but on small scales it's clearly not adequate. You really have much more stronger clustering in the models than in the data. So that is informative because that means you can actually start to think about how can I improve my model. But it's really to put model and data on the same footing. And that's, I think, is very important when you're doing it. You can do the same test here, but splitting your galaxies up into red and its function colors, red and blue galaxies. Yeah. Again, when doing this test, you can see that, and you should probably not be very surprised, that the clustering doesn't work at all well as function color, because color distributions are so different. Yeah. So clearly, it would be very surprising if you had the wrong color distribution and not with the right clustering. But at some level, you can learn here also what is limiting factor, and it's always the same things coming in. There's a small scale issue, the small scale is within the one halo term, where they're different significantly between blue and red galaxies. And that's good between the models and the data, because that helps you in informing what you need to do. So initially here, what you can see, the Galfond provides clustering which has trends similar to gamma. The stellar mass dependent clustering is there, but it's weaker. Actually, you can see here, you can see that you have stellar mass dependent clustering in the models, because when you have these curves are not exactly the same height on all the plots. It actually has them, but it's not as strong as in the data. The same is true with the luminosity. Galform is certainly very limited in the ability to model precisely the color distribution. That we knew. There's no real news, but it's something we're working now on. And a small scale galaxy clustering, because we're actually not getting the right amplitudes there. And what's informing you about small scale clustering is how you do galaxy mergers, and what's the merger scheme and the orbit tracking in there. And there's two aspects coming in here. One is intrinsic to the model, how you do the modeling of the satellites. And one thing is also, has maybe anything we did with the light cone, as I mentioned before, had an impact on how well we do the small scales. So these are two things we need to follow up. So just by looking at the Galform scale side, we can look to follow up these subhalos, if we follow subhalos instead of particles, and maybe new dynamical friction timescales once subhalos are lost. How are we actually tracking that? So that's been working on in parallel, and that was finished. They had a model to finish it and said this is the way we are doing now in the new version of Galform. We have improved the merger scheme. So I said, fine, you've improved it. Can I see what it looks like clustering wise? So this is what we've been working with a postdoc in Durham, Nuala McCullough, and where we're actually looking at the merger scheme. This is including new merger scheme. This is very preliminary, and the reason it's very preliminary is because this plot doesn't show you exactly what you had plotted in the previous diagram, and so there's many additional changes which comes into this comparison. Yeah, but the new merger scheme is that you have these trends on smaller scales that you actually do pretty well, but it's still not exactly the same ones. We need to figure out. But there are many things we have changed. We have changed simulations. So we've gone from MR7 to P millennium. That means we changed. In this example, we have actually changed the cosmology, which means that we need to retune the models. So they're not like for like, in that sense, the models. We have changed here the data set we compare to gamma to SDSS. We have changed the luminosity threshold sample to samples defined on number density as opposed to luminosity. So more checks are needed to be, but this is done independently of the merger scheme implementation that is currently being written up of this is Galform how to do the merger schemes. So you have two ways here again to see. We can indicate that things need to be improved. Improvements are done. That is a model aspect. And then you decide, okay, how we look at it, does it work well and so on. It's a separate thing. It's not trying, the new merger scheme is not trying to do this. That's the whole thing we want to make sure. Because we want to have a physically motivated model to make sure that we actually understand how we change things. So, do I have time or not? 10 minutes. Well, I think I will go, okay, I think I will stop with this. I will do this example tomorrow because I think it's easier, because it's going to take a bit longer because there's more detail in this one. So I'll stop here asking for questions on this first part, because maybe are a question on this. And there is no questions. I can go ahead. Brilliant. Okay, I'll go ahead. Okay, galaxy groups. Mocks to tune and validate Icon algorithm. That's a completely different project. So finding galaxy groups in redshift space data is really hard. Yeah. Basically, what you have, if you look at this picture, is you have your galaxies here, which are the red position or where they are in real space, and in redshift space, they have just simply moved away. Why they've moved is because the redshift space information includes the peculiar velocities along the line of sight. It's nothing more magical than this. It's just given by this relation. Yeah. So that's hard in the first place. You have actually now your structure, which might be well confined to a halo, has now been diluted very much. Now, just to give you an idea of how much this effect is of the order of megaparsecs, the typical conversion between the object where it is and it's being moved in redshift space. But my typical size of a halo is sub-megaparsecs. Maybe a Milky Way star, 10 to 12 solar mass halo is of the order of 0.5 megaparsecs in radius and whatever-ish. Yeah? So if I move my stuff factor 2, 3, 4, 5 out of that, it's going to be harder to actually find my structures. Galaxy number density is low, yeah? So it's a shot noise issue you end up with as well. Because you have only a few tracers for your halo. Unlike when you do simulations, you have a large number of dark matter particles that you're trying to find. So it's actually shot noise issues as well. Yeah, Galaxy surveys are mostly flux limited, so hence you have a selection function that comes in. You need to model that as well. Yeah, the probability is not the same everywhere. Surveys are never 100% complete, so you need to model that in as well. So marks are key in this case to test and validate and tuning the algorithm. Yeah. So in the case of gamma, we had an algorithm which has it's a standard friend-to-friend, which has two linking lengths, one which is projected on line of sight, and one is along the line of sight. There are different conditions. The reason is simply due to peculiar velocities. You know, because peculiar velocities introduce an anisotropic situation. Yeah, and so on. And then you have the selection function needs to be modeled. And in the end, we have a model here in this standard friends of friend, which usually friends of friend has one free parameter, is your value of your B of your linking length. Here we have explicitly 5 free parameters and some model assumption. And what I mean by model assumptions is what is the shape of luminosity functions and so on. It's inherent in this way. And then we've done some work on defining tuning, the cost function, which is based on bijective matching through quality and efficiency. So that is a way of actually saying what do we think is a better function and so on. The nice thing with FOF, it always gives you an answer. Yeah, you run it, you give an answer. Great. But is that the right one? Or is that, how do you know it? So if you only have observational data, you need to figure out how to deal with that. So that's where your mock comes in. So the pretty picture moment is just to say we have 3 regions, we have lots of nice groups which can be found, but are these the real groups, are these realistics, and so on. So what they have here, these groups, this is a cone diagram, it's from Redshift, and you have 3 different regions, and and you have different size circles for the number of members in your groups, and the color coding is also for whether the masses of the groups. More yellow groups are more massive groups. So first thing you notice, hang on a minute, you seem to have a selection effect here. You have only massive groups out here. Actually, it's normal, because you will only be able to detect the biggest cluster at higher redshift because you only see the tip of the iceberg due to selection functions. So this is a natural selection function. But with your mocks, you can test this. Are you doing it right or not? Okay. So one of the first things you can ask yourself with your groups is the fraction of groups halos that are match. Because you know in your simulation what are the true number of halos, what are the true linkings and so on. And so you can ask your group finding success, which depends on what it depends on. So and what is plotted here is multiplicity on the x-axis of your group or halo, and here's a number of matched groups, a number of matched object versus number of groups and halos. So ideally, you want to be at the one line. You want to have finding all the halos irrespective of multiplicity. You want to recover them properly. So multiplicity, one thing you realize is 50% of the groups of 2 members are fake, but it improves to some level with multiplicity. It goes on up here. It's even down to 60%. There's a mild redshift dependence. These 2 panels for 2 different redshifts. You see that the curves are not exactly in the same position. There's a slight mild redshift dependence. Luckily, it's mild. That means that we dealt with the selection function pretty well. We understand that. But the matching definitions matters a lot. Where do you do bijective or central? And that's kind of like the definition of what you want. Do you want to be able to make sure that what you find as a group in your simulation is the same as in your light cone, and vice versa? Is it those direction you want? That's a bijective. Or you're matching just on the central object. I'm happy to find the same object when I found the same group because I found the same central object. That's a way of differing it up. So you can see that this has an impact on how you match it up. So the rest of the plots is just for the bijective matches. So there's a subset of all the matches. But this plot informs us, this one here, informs us that we need to do the analysis split by multiplicity and redshift, which is good because these are 2 observables. I have them as an observable at some level in my data. And what you can see here, again, is how you can test and how well you're doing. You're finding the central galaxy position, the BCG, and so on, and you can rank to some level. This tells you about the position of your group, and you managed to do that pretty well. You have some long tail, but generally speaking, you find the right ones once you have matched them correctly. So it's ignoring the fact that many objects weren't matched properly and so on. And so on. So that's one thing you can do. You can look at the inferring group properties. So is inferred underlying group mass the right one? So what you can plot here with the simulation work and with your Lycon and so on is you can actually plot what is the underlying halo mass of your group and what is the mass that you have found with your group finder for your group and comparing them. Note that these is actually quite a large range of order of magnitudes, like 10 to 12, 10 to 16. 10 to 12, 10 to 16. This is the one-to-one line. The scatter is huge for small groups. But actually, scatter is huge for nearly all the system at all redshift. It's only the biggest group you seem to be doing quite well with. Yeah, so it tells you something that it's actually not a very good way of characterizing mass. So you tell that to your collaboration members who are using your groups, and what do? They use the mass. Yeah. But you tell them also that actually, if you use luminosity as proxy, it's actually much better because you have a much better relation between the true luminosity and the inferred luminosity that you have in your group. Because that comes basically down to the fact that once you have a group with enough members, you actually have seen the total luminosity of the group. Whereas actually measuring the mass of a group is really hard, extremely hard. Here we use the velocity dispersion estimator. Even though it's calibrated and trying to do the best it can with the different small number statistics, it's really, really hard. And you have this kind of relation here coming up that actually, if you look at this plot, this is the ratio of the luminosities of inferred versus truth, and this is mass inferred versus truth. Ideally, you want to be in this one-to-one plot as a dot, and you're far from this. This is like 2 orders of magnitude in mass. Yeah. So one says you know nothing about the mass in this case. So this is an example of being aware of what the limitations are. You can't do this if you didn't have a mock to train it on. Your group finder will find all the results you want, but you don't have a feeling how bad it is or how complicated it is without having mocks. So the motivation there is actually quite clear. And this tells you why you should use one or the other. Property to trust, mass or luminosity of a group. And then the nice thing is actually you can do a cross-check X number of years later by just checking the mass calibration. Yeah? So what's plotted here is actually given the masses, you bind up your objects in your groups according to dynamical mass, and you try to infer what is the inferred lensing mass in ratio of it in one sense with respect to, so this is measurements, and this is what you would have originally. So you can actually see that in this plot, you would want everything to be in the one-to-one line, like the 0 line up here flat. This is disaster. And it shows that it's not only biased. And the nice thing with this one is that these binned data here is an independent measurement of your masses from lensing. Hasn't used your calibration method in your mock and so on. The nice thing here is actually pretty flat, the two relations. This one here, the relation here, flat, there's an offset. Yeah? But that means that the luminosity inferred masses are actually quite good. So that's, again, how you can cross-check later on with additional data how well you're doing. This is just done using lensing data. And I think I will stop here. Yes, that's where it is. So that was my last slide for today. Yeah.
It's very general.
Yeah.
So you start building these models.
Hola.
After you have the simulation, or is it part
¿Seguro?
of the simulation? Is it the end of the simulation?
So you run an n-body simulation, n-body, pure dark matter, and you create your n-body world, in that sense, dark matter distribution with it, and you don't need to worry about anything. This is the starting point. That is done. After you populate it with galaxies, the way you populate with galaxies to some level is to use the information over the merger trees from these simulations. So they are totally separate. So the thing which we don't talk at all is the interaction of the baryons would have on to the dark matter, which is the whole thing you can do with hydrodynamical simulations. Because we have decoupled this totally.
And the God form you show us
Yeah.
a
Semi-analytic galaxy information model, yes.
yes, for doing that.
Yes, that is exactly how we model. Is a semi-galaxy information model to get the galaxies in your simulation volume. Yes, it's a way of populating or creating a fake universe. Yeah, but the difference is that you have physical prescriptions to some level to make these steps in and so on. The only thing you need, actually, you don't need a simulation to do it. You can actually use pressure or extended pressure theory to actually tell you about the merger to history and so on and create that. And that's what's done initially. The only reason you really need a simulation is to provide a fake representation of it, because extended pressure doesn't give you the position of halos. It tells you how many halos and its history, but doesn't know you how they are distributed in space. Simulation does that. But the simulation gives you also the whole merger to history bit. Yeah?
So from your simulations, you have the mass, right? And then you're inferring a mass luminosity relation in order to know the luminosity. Is that right?
So in the simulation, I have the stellar mass, I have the gas, I have the whole SED of the galaxy. So from the SED, I can infer the luminosity of the object.
Okay.
Yeah. So the test we did there was just to say how compatible is these color luminosity relations to give a stellar mass with respect to the model we are using. Yeah. The main reason for that is just to have a feel for, are they really well, or are they really good approximations or not, or is it there's a scatter? I think there's two parts you want to see from that plot, is the fact that there's a scatter, different models behave differently, and there is different trends for different populations. So I'm not saying that the model is the right one, far from that, but it gives me an idea that possibly my measurement of stellar masses is not as reliable as I maybe think they are either.
So what you are seeing is that the luminosity is better fitted to observations at any mass.
So the interesting thing is the model has been tuned to actually do the luminosity function and the K-band, the B-band luminosity function and the K-band luminosity function. And the K-band luminosity function is pretty much the stellar mass function, because the light in the K-band at redshift 0 is what dominates all the stars, is the star dominated. So actually you have the right stellar mass function, yeah, and the right luminosity function. It's just the fact that this meaning you get it right on average doesn't mean that you get it right on individual objects. And it's the issue with scatter and the details. Also, when you say to match the luminosity function, it's a plot which goes for several order magnitudes. It's not shown in any great detail, am I right within the 5% or 10% level? And the plot which I showed with stellar masses are actually of that order, is 0.2, 0.3 dex, the scatter. So it's just within a factor of 2, So it just gives you an idea of being aware of the limitations and so on.
I have I don't know. I have a doubt about this friend of friends you apply in the light cone, and the standard one which has only one parameter and other have more parameter. So at some limit it goes to the standard one?
So yes, it does. So the thing is, you have to have 2 parameters to some level, even if you do work in redshift space. There's nothing you can do about that. That's basically it, because you need to have a different linking along the line of sight as to perpendicular line of sight. Okay. Now, when we did the work, what you realize about just with 2 parameters, you don't do well enough. There's a limitation of how well you recover the big halos and the small halos. So it's like how you work it. There's not a group finder which is fits for everything. Yeah. So there are some additional parameters are telling you about they're minor in the game, but they are there to some level. Yeah. One of them, it tells you about how much extra weight we give to the luminosity information. Should we give more information of a bright galaxy compared to a faint galaxy when doing the linking links? So things like that is actually trying to help us to get it wants to be more informative than just the positional. When you do a friends of friends and dark matter simulation, all dark matter particles are equivalent, but galaxies are not. And we know brighter galaxies cluster more strongly. So there's some interest that if we have 2 bright galaxies should we actually make more likely to put them in the same halo or not? You know, there's some weighting towards that. The same thing we can also do some weighting with respect to colors. We didn't use color information, but there is a reason to do that, because blue galaxies and red galaxies cluster differently. So, but the main parameters, actually, there's two main parameters, and the other ones are smaller ones, which has an impact, but is not the drivers.
Thank you.
Any further questions?
So how much the Galm-form models rely on lambda CDM? Or in other words, how portable are these prescriptions to alternative models?
So if you were to do the same thing on alternative models, I think there's a couple of things. So first of all, you can say, okay, if I run it just in an alternative cosmology and I assume no change in my physics on the bionic physics, yeah, that's the starting point of it. I can do it. I would need to tune it, but the main issue actually is being able to do the simulations of the size and resolutions for this to work. I think Baojiu hasn't maybe mentioned that, but those type of simulations of 10 to the 9, 20 particles, this is kind of like nearly state of the art what we have right now. These type of here, the Millennium simulations, they are hard to do in modified gravity, you know, and this is done 10 years ago. Yeah, this is what the benchmark we worked in 10 years ago. So it's just a question of what are the so you need to push the simulation to a minimum type of mass resolution before you can start populating with Galform. And an example here, MXXL has this type of mass resolution for the halos, short of 10, just a bit more than 10 to 11. Yeah, that's not good enough to run Galform on it, because we don't resolve the halos, the merger history well enough to actually create. We can run Galform on it, but we get garbage in, garbage out. So it's just, you know, and I think, I'm not sure, this is where I need to, would have asked my colleagues who actually worked on this, how much this had been researched, this was an important mass. And I think pretty much, knowing the people who run the simulation, they knew pretty much what was needed in mass to make sure they could resolve the number of time steps and so on, the merger trees for running Galform on it, and so on. So this is an example of modified gravity are not yet simulation-wise there to be able to run it. But we could do it.
But Galform doesn't assume lambda CDM.
It's not, it does, okay. Does it assume lambda CDM somewhere? It doesn't assume lambda CDM more than it's based on standard physics in that sense. You know, like, you know, it doesn't, Galform doesn't need to know the cosmology, because cosmology tells you about it, you know. Yeah. Yeah. So you could run it in that sense, yes. But I would, the thing I'm hesitant is the fact of, not just that, it's more the fact of, given the accuracy with which we can do currently the physics limitation, adding another uncertainty regarding cosmology is just, you open up the doors for everything you can do. It's just impossible. I don't think you can rule out a model because of Galform doesn't do the right things, because I have enough parameters that probably can end up with some different definitions of what I mean is standard. You see what I mean? In the sense like it's.
I was just wondering if it was self-consistent.
It is, in that respect, it's self-consistent. Yeah.
Stop eating or just carry on finishing?
It's up to you pretty much. What you...
Okay, well, just carry on. Then I can finish.
So you want... Okay.
Yeah, I'm definitely finish too if I don't have cut.
Okay.
Where's my mouse? Oh, here.
Pero no veo el cursor.
I can do this.
No se ve nada. Ah, aquí, ya.
You should hit play.
Ya.
It's there.
No play.
Ah, yes. Good. Great. Thanks very much. So yesterday I gave a very brief overview of how PM method and AMR method can be used to solve standard gravity equation in embodied simulations. And today I build up on what I discussed yesterday and talk about how you can apply these techniques to simulations of non-standard models. As it stands, a generalization from standard model to non-standard model is very straightforward because as you saw yesterday, the equation that was used for relaxation does not require the equation being solved to be linear. So you can use that method directly, but there are some subtleties. And if you take this into account, then generalization to non-standard models will work. So I'll give a quick recap of what we got so far. So we saw that we want to solve the non-standard model equations which are generally nonlinear, and these nonlinear equations are in general not easy to be solved using techniques such as FFT. So that is why relaxation method is required. And also these non-standard models also often predict new forces which do not satisfy superposition principle, so that you cannot make a direct summation of forces produced by individual particles to get the total force. And that is why you need to solve the force on a mesh. And except for those points, there are other advantages of the AMR technique in simulations. And I mentioned two of them. One is that this will allow you to have high force resolution in high density regions. And this is actually more important for non-standard models like FFR gravity or DGP model, because those theories, you really need very high accuracy to solve the new force in those regions. On the other hand, this AMR technique also allows you to not waste too much time solving gravitational force in low density regions where resolution requirement is not high. So it has a dimension of efficiency. It can improve the performance of your code. And this is also very important for non-standard model simulations, because we will say later that those simulations are generally much slower than standard gravity simulations. And so any savings, any improvement of efficiency will be appreciated. So this lecture, I'll talk about how you can apply these techniques to two classes of non-standard models. And these are both scalar field models, one with scalar field of interaction potential V of phi. The other is a scalar field with a derivative coupling with itself. So the first half of this lecture will be about how to apply the simulation technique, relaxation technique to these classes of models. And then I'll talk about some challenges facing the simulations of these models and what kind of alternative methods. These are generally approximate methods that you can employ to tackle those challenges. So before going to the equations, I'll first talk about the quasi-static approximation. This is important actually because with or without this approximation, the method that we need to use to solve the equations will be different. So I'll start from this scalar field equation of motion. This is the Klein-Gordon equation which we saw in the previous two lectures. And you can separate actually this equation into a background part and a perturbation part. So basically you separate the scalar field into a background part which does depend on time only, and the perturbation part which describes the fluctuation around the background mean. And then you will find the background equation, which is this one, and you can subtract the background equation from the full equation to get the perturbation equation, which is this one. This is not the linearized equation. This is a nonlinear equation. So you can see that this equation, if you compare it with standard Poisson equation, you will notice that it has these additional terms, and these are time derivative terms. If you want to make it similar to the Poisson equation, you only want to keep these purple terms, and that is, you want to neglect these time derivative terms, because this will make this equation a wave equation rather than an elliptical equation. So the quasi-static approximation basically says that we can neglect these terms as compared to the spatial derivative terms. And if this is possible, then the equation can be greatly satisfied, and you can use the relaxation technique. The argument for using this quasi-static approximation is that in general, in many scalar field models, the time evolution of the scalar field is not very fast. And if you consider simulation, each time step is a very, very tiny fraction of the cosmic age. And as a result, during this simulation time step, the change or the time evolution of the scalar field is even smaller. So for that reason, the time derivative terms in this equation are generally much smaller than the spatial derivative terms, unless you look at very large scales, of course. And under that circumstance, you can neglect these terms, and you get this purple equation, which is an elliptical equation. And then you find that this equation has a very similar form to the standard Poisson equation, which means that you can actually solve this using relaxation method if you supplement the system with suitable boundary conditions, which we know is a periodic boundary condition for the cosmological box.
Excuse me, before doing that, you can introduce the background equation there and just eliminate some of the terms.
These terms? Yes, actually you can.
No, the other term. That one?
Which one? This
that
one?
And the first term in the right hand side.
Yeah.
Those are eliminated because you have the background equation.
What do you mean by limited?
Oh, I see. You are.
So this is the original equation. I take this background term from this original equation. And this gives the perturbation of this term, actually.
Okay.
These two gives the perturbation of this term.
So you are not splitting the equations in background
And
the rest?
yes, that's right.
Okay.
So let's recall what we saw in the last lecture. This is a basic sketch of how the AMR algorithm works. So you start from the particle initial condition. You calculate the density field on the mesh. If you have AMR technique, you can calculate, you can refine the meshes to get refinements like these ones, and calculate the density on the refinement as well. And then you use relaxation method to solve the potential on all these refinements. And then you make the finite difference of the potential on the mesh to calculate the gravitational force. And then you use that force to update particle velocity and particle position. And if you do this again and again into the final redshift, you are finishing the simulation. So the question now is, where do we want to add the solver of the new equation, the scalar field equation, to this whole picture? And that is quite clear. If you look at this scalar field equation and this Poisson equation, you will see that the Poisson equation depends on the scalar field. So that means that the scalar field has to be solved before the Poisson equation is. On the other hand, if you want to solve the scalar field equation, you see that it depends on the density field. And that means that this equation must be solved after you have got the density field. And that means that the new equation solver will be added between these two atoms, and that is here. So what you do is that you just, if you have your ONPM code already working for for the standard Poisson equation, you just add this new subroutine to solve the scalar field equation before you go on to solve this Poisson equation. So that is very straightforward. Yeah. So I think I have talked about this already. Got some notes. And we will say that the multi-grade method that we discussed last time is actually applicable to not only the standard gravity equation, but also these modified equations. So that is very nice. Because of that, I will not go to details of this technical again. I'll just focus on what is new in these non-standard models. So basically, the only thing that you need to be really careful about is you need to discretize your non-standard field equation in the correct way in order to solve it. And this is actually not very trivial, because if you do it wrongly, then you will find that you have a lot of numerical problems, which means that your relaxation method will be difficult to converge. It could diverge, there's instability, and so on. So I first talk about the case of a scalar field with a self-interacting potential. This is a simpler case. So I'll start from these two equations. These two are coupled equations. The first is the scalar field equation, and the second is the Poisson equation. I say that the Poisson equation here contains a Laplacian term, which is sometimes not very convenient, because that means that you need to take the finite difference in order to get the source of the Poisson equation. So what you can do is that you use the scalar field equation first to replace this term in the Poisson equation, and then the Poisson equation becomes something like this, which depends only on the scalar field itself, not its derivatives. I mean, this is just for convenience. It's not necessary. I'm sure if you do this, you can still get the right answer. And also, in many cases, like in the chameleon model or other coupled dark energy models, often you can find that these terms, they are either not important or they cancel themselves approximately. So in many cases, you can just neglect them. So that can simplify your equation. And then you get this set of simplified two equations. And the next step is to discretize these equations. You know how to do this for the Poisson equation from yesterday's lecture. And now what you need to do is just for the scalar field. And you can do this similarly to the Poisson equation. So for example, if you want to calculate the first derivative of the scalar field, you use 3 cells. You can calculate the first derivative as the difference between the value in this cell and the value in this cell divided by twice cell size, and so on. So you can do this for the second derivatives and other terms. And that will give you a discretized equation, which basically I define this operator L, which is a function of phi ijk, and this operator is written here. So you can see that it is very similar to what you saw for the Poisson equation. The only difference is that now there are terms here in the green boxes which are functions of phi ijk, and these are nonlinear functions. So in the Poisson equation, the first line is the same, except for the symbol, of course. And the second line will be just the density field. Here you have nonlinear functions phi ijk. So this is where the nonlinearity of the equation kicks in. But this is not a problem, because as we discussed already, this equation which you use to update your old guess to get a new solution of the phi actually does not assume your your operator L to be linear. It can be nonlinear. So this actually is not a problem.
What happens if you have several roots? So you have several solutions to this.
We have several what? Several roots.
Yeah, several roots. You were explaining yesterday about comparing to the Newton method.
Yeah.
So you can have a situation in which in a cell you have several roots. I don't remember the equation exactly that you wrote yesterday.
Right.
But it is clear that you can have several roots. So
I'm not sure you can have several roots because, I mean, this
okay,
is a
you have,
partial
you
differential
have
equation.
unicity of the solutions.
Yes,
But-
once you
but-
fix
but
the
that's-
boundary condition,
but that is differential equation. So you have unicity of the solutions, but when you discretize, you can lose the unicity. So
And-
what I'm meaning is that it is possible, I think, maybe not, that you have several solutions to the relaxation equation.
I understand your question. I have never seen that problem. So what I can say is that from a theoretical viewpoint, that situation should not happen because once you fix the boundary condition, the solution should be unique. And
Yes, but
experience also shows that I never experienced any problem with multiple solutions.
okay.
Yeah.
Yeah, but at the time of discretization, you can arrive to the situation. So it is possible, I mean. I don't know if it happens.
I don't know, maybe it's someone you know.
It definitely can happen in differential equations. I mean, it definitely happens in PDEs that if you're using the Newton relaxation method.
Yeah.
If you're not sufficiently close in the iterative procedure to the exact solution, because you use essentially, you start with a certain trial, and then you relax. So if you're not in the basin of attraction of the solution, which is essentially a question.
Yeah.
If there are multiple routes and you're in the basis of attraction of the wrong route, you will simply run away from the exact solution. So a lot depends on how touchy the actual nonlinear solution is. For example, if you're doing things like a nonlinear sigma model, which I looked at, it turns out to be extremely tricky. You have to be really careful. But in these cases, probably the equation is just much nicer. The basin of attraction of a true solution is large enough that you're always inside it. You're not running towards false solution.
Unless your initial guess is too off.
Unless your initial guess is too high.
Thank you.
Right. So one thing that is important in this kind of relaxation method is that the scalar field sometimes its value is very small. So like the chameleon model, the scalar field is trapped close to zero, and that means that its value is always small, and also its value cannot be negative. It can be only on one side of the zero axis. And that means that numerically you could run into a problem because if you have an old gas of phi which is small, correct? Then this numerical value in this box, this is the correcting term that you add to get the new gas. And this numerical value, there's no limitation on it. It can be big. If it is large, then it could make the new value of the scalar field negative. And then that means that some of your functions, for example, the potential or the coupling function, they may not be defined in the negative domain of phi, and then they could run into problem. So what people normally do is that they define a new variable, which is a logarithmic of phi, and then this will guarantee that this u will always be, it doesn't matter, it could be positive, it could be negative. So the problem with that is it adds more nonlinearity to your equation. You can say that now with a new variable u, then phi equals e of u, of course, then the derivative of phi will contain e of u, and similarly the second derivative will contain e of u. So the discretized equation will be much more complicated.
So can't you use some limiter in the previous equation rather than doing this?
That is also possible, yes. I think someone is trying that. I don't know what is the performance. That's definitely one possibility. So then this equation will look much more complicated, and you have these nonlinear terms. And this, I mean, the advantage of this is that you will always guarantee that your functions like the v and c functions are well defined. But the drawback of this method is that you are nonlinearized and already nonlinear equations. You are adding more nonlinearity, and you make the relaxation method even slower, even less to converge. So that is why these kind of simulations are generally much slower than standard gravity simulations. The next case is the scalar field model with derivative couplings. And as a reminder, for this kind of model, you have this sort of equations where you have the standard term of kinetic energy, the kinetic term of the scalar field. You have coupling with matter, and then the scalar field couples with itself through these complicated nonlinear terms. And I want to mention that these are not higher order derivatives. These are just higher powers of second order derivatives. So I'll use this so-called Dirac-Gabadats-Parati DGP model as one concrete example. So the method described here will apply to other types of model with derivative couplings. And for that DGP model, the equation looks like this. So you have here as the nonlinear term, you have a combination of Laplacian phi squared minus derivative I derivative j phi and phi ij. So this is how the equation looks like. So if you want to discretize that equation, then you will face this new term. And this term, you already know how to do the discretization. For this term, you need a scheme to discretize it with the same level of accuracy. And if you want to use second order accuracy, like for the standard derivative like dx phi, you know that this discretization depends on the phi value in these three cells. Well, for dy phi, similarly, the discretization will depend on the phi values in these three cells in the y direction. But if you want to discretize this dx dy phi, then you will find that its value depends on the scalar field in these four cells. So these are off-diagonal cells, not direct neighbors. And I will use blue to highlight these are off-diagonal cells, while I will use red color to show direct neighbors.
Excuse me, a general question.
Mm-hmm.
Within a cell, the gravitational potential is constant?
You only define the gravitational potential or the scalar field at the center of the cell.
And it's constant within this h squared or h to the cube volume. Do you have a small h in the previous?
Yeah, the h is the cell size.
Yeah, right.
Yeah.
Within this cell size, all the quantities are constant?
I don't know why this is important. Is it critical for some consideration?
I just was thinking if you have a fit force,
Yeah.
the range of the fit force should be longer than this small h.
Yes,
It is normally the case.
it is normally the case. But what you do is that you have, let's say if you want to calculate the fifth force, then you take the gradient in these two cells.
These two cells, yeah.
Yeah, so for that reason, I don't think it's a constant inside the whole cell. It's just like a linear change from one cell to another. So, okay, so we want to apply the relaxation method, and now we want to say, if you discretize this equation, then how does L depend on phi ijk, and that is important. So to do that, we will separate the di dj phi, the second derivative of phi, into two parts. The first part is only non-zero when I equals j. So this means that for this part, you only need to consider these direct neighbor cells. For the second part, I use over bar to denote it. It is defined such that it is 0 if I equals j, and if I equals it does not equal to j, then it is equal to nabla I and nabla j phi. So I will make sure that by this division, by this separation, the first term will only depend on the direct neighbors, while the second term depends only on the off-diagonal cells. By doing that, the advantage is that the blue term, because it depends only on the off-diagonal cells, it does not depend on the center cell. And the center cell is basically phi ijk. So then all the dependence of phi ijk will be in the red term. The blue term, don't worry. And by doing that, this equation becomes slightly different. Instead of 1 in front of this factor, now you have 2/3. And now this term becomes with an error over bar. So that means that this term does not depend on the central cell. And then what I do is that I consider this equation as a quadratic algebra equation of this variable. So I can first solve it. I solve this equation. I get one solution, two solutions, two branches of solutions, because this is a quadratic equation. And I define, but in this process, I define variables alpha, which depends only on background quantities, and a sigma, which depends on the blue term and the density term. And the important thing here is that the sigma term, because it contains only the blue term, it does not depend on phi ijk, the scalar field value at the center of the stencil. So the next thing that I can then discretize this new equation. So the first term, the red term will give you the standard discretization, and then you also discretize sigma. Well, this is more complicated, but the important thing is that this quantity does not depend on the center cell. And because of that, after discretization, the only dependence on phi ijk is here. So this is basically a linear equation for phi ijk. And then you can do the relaxation. Because this is a linear equation, so this is much faster. And that is basically how you, so that is actually the most important part of solving this type of equations. I mean, once you have done that, solving this equation using relaxation is trivial, basically. But before you do this, I mean, you will find all sorts of numerical problems. Not all sorts, some sorts of numerical problems. So this is an example of the simulation of this model. And I have 3 models simulated here. These are the particle snapshot from redshift 0. So this is standard gravity, density field, high density regions in white color and low density regions in black. The second panel shows a model in which I artificially removed this nonlinear term from the whole equation. And then this is a model in which I solved the full equation. So, of course, if you look at this method distribution, visually there's no difference. But if you measure the power spectrum and calculate the relative difference from lambda CDM, then you will see a big difference. So this is the case where I drop the nonlinear term. You can see because there's no nonlinear term, the difference from lambda CDM increases if you go to smaller scales. And this is the full case. In this case, you have the nonlinear term, and the nonlinear term helps you to go back to lambda CDM on small scales. So that's why on small scales, there's no deviation from lambda CDM. Yeah, on large scales, you have the difference. Remember, this depends on the parameter, of course, on the model parameter. But the point is that this is a Weinstein type of model. So for Weinstein type of models, if you remember what I discussed in lecture 1, the deviation from standard gravity only happens beyond Weinstein radius, and that is on larger scales. Within Weinstein radius, the difference from lambda CDM becomes vanishing. So this is exactly what you see here. So no difference on small scales, difference on large scales. Good. So now I come back to the quasi-static approximation. So in the beginning of this lecture, I said that I want to use quasi-static approximation because these terms are annoying. They make the equation a wave equation, which means that you can't use relaxation to solve it. And I gave justification of this approximation. So this approximation works fine for chameleon type of models because the scalar field value is always small. It's small everywhere as well. And that means that the time derivatives will be negligible. So for those kind of models, you do have a good approximation if you neglect those terms.
And what redshift do you need the
It changes always very slowly. So,
So
yeah.
you need it all the way from the set 1000, 10 to the 6.
Yeah, from like maybe
From the picture.
from the very beginning to today. So
The very beginning for you is 10 to the 6?
could be higher, could be
Or
higher.
even more.
Yeah, it doesn't matter. The point is that for this kind of models, the scalar field always takes a very small value everywhere, no matter which time you look at it.
Those are the ones that you're actually thinking now. I'm just trying to be more general. So, for different models, from which redshift would you need to apply all this to be slowly varying the skeletons?
So it also depends on the model itself. I mean, I will show one model, in which case you
understand, but I mean,
yes.
For this work, I mean, what is the largest redshift that you start working with? In order, which redshift do you start needing to have these fields to vary slowly? Set 10 to the 6, 10 to the 12, 10 to the 18, or 5, or
It doesn't make a difference for me because for the simulations, I only concentrate on low redshifts, like after redshift 100 also. So as long as in this redshift range, the variation is small, I'm fine.
So,
Yeah.
so from 100.
Could be higher, yes, but this is enough for me.
Huh?
This is enough for me. So, okay, so this is a test of the effect of that quasi-static approximation in one of the models, the FFR gravity model, which is a specific case of chameleon model. Here I'm showing the relative difference, relative enhancement of matter power spectrum as a function of length scale. So this is what you normally see in FFR simulations. On large scales, there's no difference from GR. On small scales, you see some difference. And the red symbol is the case with no quasi-static approximation, while the blue case is the case with quasi-static approximation. So you can see that, okay, so this panel is a low resolution simulation, and this one is a high resolution simulation. You can see that the effect of quasi-static approximation is indeed quite small for these sorts of models. So that means that it is safe, at least for this model, for chameleon models, to use quasi-static approximation.
But what is the size of the box here?
The size of the box is that there, yes, I count. 256 megaparsecs, 128 megaparsecs. So these are much, much smaller than the cosmic
Yeah.
volume, of course.
When you really go to big boxes, you will need to include that. I mean, cosmological
If you,
simulations,
yeah, so
something like that.
by using these small boxes, of course, you are missing the large scale modes. And for the large scale modes, time derivative may be important. But the important thing is that for this sort of theories, you can already say that on large scales, there's almost no difference from GR.
Yeah.
So you don't really worry too much about that.
Yeah.
What model is this?
Someone,
What model is this?
what model? This is FFR gravity.
Yeah, but which one?
This is FFR not equals 10 to the minus 6, I think, if I remember correctly.
Sorry?
FFR not equals 10 to the minus 6. So this is a case with a very strong nonlinearity. Okay, so there are other theories in which the time derivatives actually cannot be neglected. I will show one example just a few slides later. So for this kind of models, if you want to do an n-body simulation properly, then you need to solve the full wave equation. And that means that you cannot use of this scalar field equation with the geodesic equation of matter particles. So basically, this is x is the particle position, and this is, of course, the acceleration of the particle. This is the frictional force due to the expansion of the universe, and this is the gravitational force, and this is the new force. So this basically describes how particles move in time. What people do in n-body simulations is that they separate this second-order equation into two first-order equations. They define a new variable, which is basically the velocity of the particle. And so, of course, the velocity is the first derivative of the position, while the velocity's derivative is the force. You can do something similar as there. So for this equation, you can define a new variable chi, which is basically the first-order time derivative of the scalar field. And then you have an equation for the new variable chi dot chi. once you have done this, you can make an analogy. You can update phi and chi as what you do for x and v in embodied simulations. So this is an explicit time integration scheme. And you can use even the same time stepping scheme like leapfrog. So you update positions at full time steps, you update velocities at half time steps. Similarly, for this scalar field, you update the scalar field itself at full time steps, while you update the time, its first derivative, the new variable chi, at half time steps. The only difference is that particles can be anywhere. They can be anywhere in the box, while for the scalar field, you only do this at the centers of the cells. But that is trivial. So this is an example of that method. And before that, I just want to have 1 minute to recall what we learned from this situation. This is the so-called symmetry model, which I discussed briefly in my first lecture. So the symmetry model is a scalar field model. Its potential has this symmetric form. So originally, in high density regions, the scalar field is trapped at the center, at the very center of this potential. But at low densities, the scalar field could roll down to this minimum. And the thing is that the scalar field could, by doing this, the scalar field could change a lot in time. So from here to here is a lot of change in the scalar field. So that is why the time derivative cannot be neglected. And what is more interesting is that the scalar field, when it rolls down the potential, it can choose either direction. It can choose to settle down at this minimum or this minimum. So it can choose to do this at different places in the universe. And that means you will find that the scalar field will take different minimum values in different regions. So this is one example. So at this redshift 0.8, the scalar field takes a positive value, which is red. So this color bar is the scalar field value in this region, while it takes negative values in the rest of the box. And so, of course, these regions are not separated. They are not insulated from each other. So they interact and they try to compete with each other. And in this situation, in this simulation specifically, you will find that this region loses the competition. So its value becomes less and less positive, and in the end, it is conquered by the blue region. So that basically this region disappears, and the scalar field originally takes this value, but then it takes this value. And
The numbers are megaparsecs?
Megaparsecs, yes. So you can see some interesting feature. You can see that as the scalar field changes value, you can see these arcs. These are the imprints of the scalar field waves. The scalar field has a wave. It is a wave equation. So the scalar field propagates from this region to this region. And in the end, in all places, the scalar field takes a negative value there.
Is there any imprint of these features?
Any imprint? I don't know. They did in this paper. These people, they don't really give an example of how this can.
Look at these domain walls there.
Mm-hmm.
It should make something to light passing through it.
But you don't know how to observationally detect this domain wall because you don't observe the scalar field directly. One thing is that at the boundary of the domain wall, the scalar field changes dramatically. It changes from this value to this value. Yeah. So that means that the spatial derivative of the scalar field could be quite large at the edge of the domain wall, and that tests this effect. Good. So I've discussed some of the commonly used n-body simulation techniques for non-standard models, and here I want to summarize its main limitation, which is what I already said. Basically, they are very slow. This is, again, because these equations are nonlinear, and relaxation method works more slowly for more nonlinear equations. And I can give you one example. In the highest resolution simulations of FFR gravity that we have simulated so far, for each simulation, we always do a simulation of the standard model with the same specification, the same particle number, box size, and so on, the same model, same cosmological parameters, except with a difference of gravity. So that high-resolution simulation for alpha gravity took about 15 times longer than standard lambda CDM simulation. So this is quite slow. It is actually not acceptable. I mean, you can do one simulation of this to study some of the properties of the scalar field, but if you really want to do big box simulation like what Peter said just now, then you'll be running into problem. So this is particularly a limitation for like galaxy surveys, because there you want maybe to run a large number of simulations to estimate the covariance matrices of variables, and this is not practical. So for that reason, it is important to, on one hand, try to develop improved methods, optimized methods for embodied simulations, but on the other hand, to develop alternatives to embodied simulations, basically approximation methods, which can give you results you want more quickly. So here I want to give you a few examples. I mean, this is not a complete comprehensive overview, of course. I want just to give some examples to say how you can speed up your numerical simulations with some approximations, or how you can use other approximation methods. And these methods, because they are approximate in nature, so if you use them, you need to be careful to understand their limitation, of course. So the first method that you can use to speed up your simulation is what we call a truncated simulation. And the idea is very simple. So here, to understand why embodied simulations for non-standard models are so slow, okay, of course we know it's slow because it's nonlinear equation, but also it's slow because you have a lot of refinements. And on these refinements, resolution is high, which means that it is even more difficult for the relaxation method to converge because the density field could fluctuate a lot. So indeed, we find that in these kind of non-standard simulations, at most of the computational time is spent on solving the equation using relaxation on these refinements. And there are many, many levels of refinements. For all of them, you want to solve the equation. So the question is this necessary? I mean, do we have to solve this equation on all these levels? So we have seen that in these non-standard models, you have a new force, and these refinements are good for solving that new force. But we also know that this new force, if you want it to pass solar system tests, you want the new force to be small in high density regions. That means that on these refinements, the new force is small. So we are actually spending a lot of time solving something that is small to make it accurate. And so the guess is that probably this is not completely necessary, because if you have a small quantity and you have some error on it, maybe the impact is not significant. So for that reason, what we can do is that we can stop solving the non-standard equation on these refinements. Instead, we use the scalar field value on the cost level, on the lowest level, and we do interpolation to get its value on final levels. So we still end up with some scalar field configuration on the refinement, but this is just from interpolation from lower levels rather than from a true relaxation solver. And because you have the scalar field on these refinements, you can still calculate the new force on the refinements, which you can use to update particle positions, which is nice. So what is the result? Okay, so this is a test for the DGP model again. And so on this plot, I show the relative enhancement of the matter power spectrum with respect to GR as a function of length scale. So this is small scale, this is large scale. Again, you see that on large scales, you have a big difference from GR. On small scales, everything goes back to standard gravity. So the different colors, the blue color is the full simulation, which means that I solve this equation on all refinement levels. And then, sorry, the purple is the full simulation. And then from blue to green to red, I gradually stop solving the equation on lower and lower levels. So in that case, in this red curve, I only solve the scalar field on the lowest level. And I use interpolation to get its value on all other higher levels. So what is the impact? The impact is actually quite small. You can see that up to like k equals 5, there's almost no difference. So the difference in power spectrum is below 1% up to k equals 5. So that is, in my opinion, acceptable because down to this scale, you already see a lot of other complications. Like for one thing, you have baryonic effects which can impact this, which you don't have, of course, in these simulations. And also, there are different simulation codes, and they do not agree actually better than 1% down to these scales.
In these simulations, you have this scalar field, but also dark matter.
Mm-hmm.
All right.
Yeah. So if you look at the halo properties like halo mass and halo abundance, halo profiles, the agreement between between the worst case scenario and the full simulation is actually within 3% accuracy. And if you look at the halo positions and halo velocities, the agreement is even better. It's like within 0.05%. So this is actually quite a good agreement in terms of simulations. Now you want to know what is the savings from these kind of approximations. So this lists the CPU time that is used in all these simulations. So this is the lambda CDM CPU time. So for the full DGP simulation, it takes like almost 14 times longer than lambda CDM. Well, in the worst case, in the red case, where you truncate very aggressively, you find that you only take like 50% longer than lambda CDM. So this means that by doing this kind of approximations, you don't really lose a lot of accuracy, but on the other hand, you get a great boost of the performance, and this makes the simulation almost as efficient as standard gravity simulations. That can be useful in, yeah. For this one, we use, okay, so this is based on experience, of course. So we know that for a given resolution, we can truncate at that level. And this is learned from this kind of convergence tests. How do you interpolate? So there are different interpolation schemes. So if you go from a cost cell to a fan cell, I don't know whether I have this. So for example, this is a cost cell, and this is a fan cell. You want to get the value of the scalar field here, and you know the value here. So what you do is that you use all the nearby cost cells to find the gradient of the scalar field on the cost level. And then you can use that gradient to say how much the scalar field changes from here to here. So, okay, so we have tested this truncation methods for different kind of models, and for the DGP model, we have seen that it works really well. But unfortunately, for all the other types of models that we have tested, it doesn't really work that well. So the improvement of accuracy, sorry, the loss of accuracy is terrible for those models, and for that reason, this method is quite limited. Yes.
In these simulations, you are using in the expansion of the universe numerical constant, right?
Mm-hmm.
Yes.
No, it's not the cosmological constant. It's a modified gravity.
Just for the expansion.
Just for, yes, that's right. The expansion rate is lambda CDM.
Okay, but because the equations are non-linear, you can have back reaction effects.
That's true. You can have back reaction even in lambda CDM. So,
Yes, yes, that's true.
Yeah.
But in lambda CDM in GR, not in lambda CDM in Newtonian lambda CDM, you don't have any back reaction effects.
Okay.
Okay.
Mm-hmm.
But in this scenario, you can have back reaction effects even if you are using the Newtonian limit. Because the new equation, the new Poisson equation, is non-linear.
Yeah, but that is already taken into account in the scalar field equation solver. So I don't see any explicit additional term that you should add to the equations you want to solve here.
I don't see that, but I think that can happen. The fact that you don't have back reaction effects and Newtonian gravity, that the equation is not linear. In GR that doesn't happen, so you have back reaction effects. So now your new big force or your modified Poisson equation is non-linear. So at least the beta parameter is a constant.
It's a time-dependent function.
Yes, it's in the original chameleons it is a constant.
Okay, yes.
So I am just wondering if you have thought on that.
No. There's no. I mean, if you want to start look at back reaction, then probably it's best to start from lambda CDM itself, from GR itself.
Because in GR you have back reactions.
Yeah, but
It has,
can
I
that
don't know why you're so confident if you have bad reactions. Actually, it's not clear because
I am not following confident.
but I think, yeah. So right. So actually, there is nothing saying that there has to be back reaction in GR. So you can do full GR perturbation.
There are back reactions.
No, not true at all. I mean, this is a highly complicated situation because a lot of the calculations that were done earlier were wrong. They were wrong papers, certainly. So this is something we should discuss. But actually, Newtonian gravity simulations, actually, it's very important to keep in mind that if you're working in a Newtonian approximation, you are not necessarily in deep field or large scales. So there's a nice paper by Bob Wall and a student discussing
I was
this.
talking about the
Right. So that paper is the one that says there isn't a back reaction.
that we are not important.
Right.
Yes.
Exactly. Right, so they are not important in GR. So now the question is, in other situations they could be important. I just wanted to make sure that people are not under the impression that there's some catastrophe happening in GR as well.
right? So we have seen that you can do some sort of truncated simulation to speed up the simulation itself, and that can work for some models, but not all models. And another method that you can use instead of n-body simulations is to use fitting formulae. And so I guess many of us are very familiar with this kind of techniques. So for example, in the halo mass function regime, people have developed fitting formulae such as Shastoma mass function, Tinker et al. Mass function, Jenkins et al. Mass function, and these are parameterized fitting formulae that for the parameters you can calibrate with simulations, and then you can use this formula in your calculations in other observables without actually doing the simulation itself. So for that reason, this is quite convenient. And the things, can we do this also for non-standard models? So before giving some examples, I want to say that this formulae, such as the halo mass function and halo power spectrum fitting formula, they are actually they are motivated by physical considerations. So you have a simple physical model. You make some prediction from that model, and this prediction normally gives you a qualitative correct answer, but quantitatively it's not accurate, and that is why you need to add parameters to that formula, to the prediction, to make it more flexible, to make it fit observations. And you can use the observations to fit those parameters. And one particular advantage of having this kind of fitting formula is that you can have okay, so if you want to do a Monte Carlo search of some parameter space, you want to sample arbitrary points in that parameter space. So that means that for any point that you can sample in that parameter space, you need to be able to calculate the observable. And this can give you the ability to do that. In embodied simulations, you can't do embodied simulation for all parameters. You can use some other techniques such as emulators, and that is different. So I'm not covering that here. So the first example I gave here is the halo mass function. So our current understanding of the halo formation is that dark matter halos, they form from initial high density peaks in the density field. So if you have a overdensity in the initial density field, then because it's overdense, it has stronger gravity than its neighboring regions, so it attracts more matter towards it, and it grows. And the initial condition, as we know, is usually described by a Gaussian distribution. So to make that connection, you will need to know how the initially overdense patch evolved in time and finally collapsed into a singularity. And people take this collapse to singularity as a definition of halo formation time. It's just for convenience. So, okay, so the idea is that if you have a patch that is initially overdense, a little bit overdense, then the overdensity will slow down its expansion. So it should originally expand with the universe, but because it's overdense, its expansion is actually slightly slower than the cosmic expansion rate. And so it expands, but expands less quickly as the universe, and at some point, it will stop expanding because the gravity becomes so strong, it makes this patch to collapse, actually. So this is how you can model this connection from the initial density patch to the final halo. And in the simplest case, you can model this initial patch as a sphere. So you can use the so-called spherical collapse model to calculate the evolution of this spherical patch in time. And you will naively you can think that if the initial size of this spherical region is large, then you have more matter in that region, and then the halo that forms at late times will be more massive because of mass conservation. Also, if initially the overdensity in this patch is high, then you can imagine that this evolution will be faster, so the collapse will happen at an earlier time, and that means that halo will form at an early time. So given this picture, you can imagine that if you will know the initial mass and the initial size and initial overdensity of this patch that is needed so that this patch form a halo of mass m at given redshift z. And then you can calculate the abundance of initial overdensity patches that satisfy those requirements. And then you can use that as a proxy to predict the abundance of halos of mass m at redshift z. So this is how you make this connection. The idea is very simple. So if it works in standard gravity, there's no reason why it shouldn't work in non-standard models. So what you need for non-standard model is just to model the evolution of this patch in time. This could be different. So here I give you a few examples. The first example is the standard gravity. We all know that it is governed by Newtonian gravity. So the evolution is very simple. That's good. And the second case is the Van type of models, such as DGP model we saw just now. For this kind of models, it has a special property. If this region is spherical, then the evolution of this region will not depend on its environment. So this will evolve as a separate universe, although it follows a different gravitational law. So if you know that gravitational law, you can predict this evolution. For other models like chameleons, it's more complicated because even if this region is spherical, its evolution will depend on its large-scale environment. So for that reason, you need to know the environment and you need to know how the environment itself evolves. And that means that you need to evolve both this spherical patch and its large-scale environment. You can define the environment as a sphere with a certain radius chosen for physical reasons. I'll not discuss that here. But the idea is that once you know what is the environmental density, you know how the environment evolves, and you can use that to feed back to the evolution of the spherical patch. So you can co-evolve these two systems. Of course, so we have seen that if you want a halo of mass m to form at redshift z, you know its initial size and its initial over density. This is also true for these models, but then the initial size and the initial density will depend on the environmental density. So for that reason, you need to calculate that for different environmental densities, and you need to know the distribution, the probability distribution of the environmental density, and then you can integrate over that probability distribution to find average. So here is some example showing how that method works. So this plot shows the relative enhancement of halo mass function f of r gravity as a function of halo mass. Large mass here, small halo mass here. These are three different parameters of FR models. Symbols are simulations, and curves are different versions of the method, different implementations of the method that I described just now. You can see that these methods, they give qualitatively reasonable prediction, but quantitatively, they are not very accurate. They're actually quite inaccurate. So what you do is that you can try to generalize those predictions from the method I described here, and then you introduce new parameters, give the formula some freedom, and then you use n-body simulations to calibrate those parameters. So this is the result of the calibration for the same three models. These different colors are different redshifts. You can see that if you do this calibration, then the halo mass function formula can agree with simulations. Simulations are these shaded regions much better. And actually, by doing this, my colleague Cantanillo has been able to make the fitting formula agree with the halo mass function prediction from simulations within 3% accuracy. So that is quite good. So finally, I'll use the last two slides to mention a fitting formula for the metapower spectrum. And for that, I guess this is very known that we have this so-called halo fit model. It is based on halo model itself. So the original idea is that, the metapower spectrum is basically the Fourier transform of the two-point correlation function between different places, between overdensities at different points. So it can have two contributions. If the 2 points are separated by a large distance, then they are most likely belonging to different dark matter halos. So these are what we call two-halo term. In contrast, on small scales, if 2 points are separated by a very short distance, then it is more likely that they are belonging to the same halo. So then you have this so-called one halo term, and then the correlation function can be calculated by assuming that the halo density profile is, for example, NFW. So this is an example of the halo mode prediction of the metapower spectrum, and the solid line is the total nonlinear metapower spectrum. It has two contributions, the one halo term, which dominates on small scales, and the two halo term, which dominates on large scales. So the three different colors are three different models. I guess you will know which one is standard gravity. So you can see that this model gives a quite good qualitative prediction if you compare it with simulations which are symbols of same color. But it's not always accurate, especially at transition between one halo term and two halo term. You can see that it is not very accurate. So what you can do is that you can make some generalization. You can add more parameters to this prediction to make it more flexible, and then you use simulations to fit those parameters. And this is what people do in halo fit. Similarly, for non-standard models, my colleague Gongbo Zhao did a modified gravity halo fit, and this is the result for f of r gravity. Again, the vertical axis is the relative difference of the metapower spectrum in f of r gravity and GR. horizontal axis is K, small scale here, large scale here, different colors, different models, solid curves, halo fit, and symbols are simulations. Different panels from top to bottom are different redshift, from redshift 0 to redshift 1. On the left, you have Planck cosmology. On the right, you have WMAP 9 cosmology. So the basic idea is, if you look at this, you can see that the halo fit formula, which is basically the solid curves, could agree with simulations quite well. So you can actually use this sort of halo fit formula in the calculation of other things, such as matter power spectrum, Lansing convergence power spectrum, Lansing pi spectrum, and so on. And by doing this, you will not need to use simulations, and you can still get reasonable accuracy. So finally, there are many other methods to approximate, to replace simulations. And some examples are remapped simulations. I don't know whether many of us have heard about it. You can use the Dulwich displacement of particles from the initial condition to get the final snapshot. You can use second order Lagrangian perturbation theory to do that. And these kind of things, you can do them instead of simulations. They can give you some qualitatively reasonable result, but they are not accurate quantitative level. As a result, if you want to use them, you need to understand their limitation, and that will help you to avoid making too aggressive conclusions. Thank you very much.
Just different deviation from lambda whole dark matter.
What,
As
sorry?
an approximation.
Yeah, I can hear you.
Yeah, no problem.
Yes. To test different models, non-lambda whole dark matter, in an approximated level, which of the different options would you recommend to test these models?
Which of these alternative methods?
Yeah, I mean, what would be fast enough just to see more or less what it's doing before doing a full calculation? I mean, a full simulation.
So, I mean, for these kind of things, they are quite useful. I mean, I didn't show the lower panel of this plot. Actually, if you look at, although the power spectrum prediction by the halo model is not very accurate, if you look at the relative difference between different models, the theoretical prediction agrees actually better with simulations. So, for me, I would use this kind of analytical methods first to get an idea about what kind of deviation, what quantitative level of deviation I can expect for the different models. And after that, I can decide in which parameter region it is worthwhile to run simulations which are more expensive.
One more in the back.
So you're using this Husavitsky's model, right? With these parameters for the derivative of today, right?
Which model, sorry?
You are using this Husavitsky's model with these parameters that you are fixing, and you are changing this parameter. So, but this is the most similar model to lambda CDM, and I think that it is a good assumption to have the background of lambda CDM for this particular model. And if you change the FFR model, I don't know if you will have the same behavior. And I mean, when you are taking the quasi-static limit, I think that it will change. It will be more important. And also, if you change, because you need to change also the background. And I have another question. How do you fix the initial conditions for this, for your simulations?
Okay, so let me answer your first question first. So here I'm showing this specific model, but in that paper, if you look at this paper, we did check this for different models that cover the whole range that is allowed by observations currently. So this good agreement between quasi-static approximation and no quasi-static approximation holds for other models as well. Also, you mentioned that these kind of models have lambda CDM background.
Yeah, you told, well, that I heard that you said.
That is true. I mean, for chameleon type of models, you can show that you have to have lambda CDM background or very close to lambda CDM background, because if there's a slight deviation of the background evolution from lambda CDM, then the model will run into trouble in local
With
tests.
observations, yes.
Yes. So for your second question.
But in the past, I mean, maybe we can have a very similar lambda CDM model until redshift 1.5, and then we can have some differences. And we don't have observation for that. So.
That's true. It really depends on your model. I mean, in the symmetry model, it could be like you may have this property. I mean, and for your second question about initial conditions, so in most of my simulations, I use the same initial condition in modified gravity, non-standard models, and lambda CDM. And the reason for that is, for the initial condition, I normally choose somewhere between 50 and 100, and at those high redshifts, any effect from non-standard model is expected to be small. So if you assume that your cosmological parameters are already fixed by CMB, then there's no reason to expect a big difference of the initial conditions in the different models. Now, I'm not saying that all non-standard models will have the same initial condition. I'm just saying that this is true for the models that we studied so far. There are models which can give you, which can require different initial conditions. I agree, yes. And for that, probably you will need to modify your Deutsche approximation or some better method to generate initial conditions for those models specifically.
Okay, thank you.
Any other questions before lunchtime? Okay, put it that way, I guess no. Okay, thank you again.
Very nice.
So I'm gonna give few announcements. Not everybody have signed this thing, so please do it, because we need to have all the signatures, if possible, today. And the other thing is